All right, super. So we're delighted to have Jacopo here again for the second of the two talks. Thank you all for coming. I think without further ado, Jacopo, please take it away.
Thank you. So it's a pleasure to be here for this second talk where I can now go into the details of thermalization, and in particular of my work on thermalization at next to leading order, which I will explain in a while. What does it mean exactly? So just to give again as an introduction and connect to the previous talk. So the big question here we want to address is how systems which are initially not in thermal equilibrium approach thermal equilibrium, and in particular systems that are described by non-abelian gauge theories such as QCD. So that's an important question, of course, in heavy ion collisions, as we saw in the previous talk. But it's important also for cosmology and also for atomic physics. So in the case of QCD and heavy ion collisions, just to briefly repeat what we touched upon last week. So the big question is, how can we describe this rapid transition from the initial nuclear state to something that's near thermal and that can be described by hydrodynamics? And it can be described very successfully by hydrodynamics. And that hydrodynamic description starts at an initial time that it's not tau equals 0, which would be the moment where the two nuclei are touching each other, but rather some non-zero finite but small initialization time of the order of the Fermi over C. So that's, for instance, the plot I showed last week from Heike and his collaborators, where calculations of the V2 and V3 for PA collisions are sensitive to the thermalization time. And you see that the thermalization time of 0.4 Fermi tends to underpredict the experimental data from CMS. So what I will discuss in this talk is, I will start by going in more detail through what I sketched last week. So the weak coupling picture of hot non-abelian gauge theory, and then the weak coupling tool to describe thermalization within this picture, which is the effective kinetic theory. And I'll be gearing up then to use this effective kinetic theory to study what is called bottom-up thermalization, which is this multi-stage process of thermalization weakly coupled, in a weakly coupled description of thermalization for heavy ion collisions. And finally, I will show how next to leading order corrections to this effective kinetic theory can be computed and give us some better understanding of theory and of its uncertainty in these studies of thermalization. So the weak coupling picture. So I showed this picture last week already, but now I can go into some more detail. So this is a figure that was originally drawn by Derek. The idea is that you should think of your plasma as being made of hard particles. So to set also the graphical notation, when these gluons with a line going through them means gluons which are hard, which have an energy of the order of the temperature. And this double line would then be for quarks. So these hard quasi-particles will carry most of the stress energy tensor, and I will discuss later the soft field modes. So what does it mean that they carry most of the stress energy tensor? It means that the stress energy tensor, if we think about the diagonal components, is the energy density and the pressure. So this means that the thermodynamics of the plasma will be carried mostly by these hard modes. And the gluonic, if you think about the gluonic modes, if we're in thermal equilibrium, then I will discuss how this is amended away from thermal equilibrium, but in thermal equilibrium, they are described by the Bose-Einstein distribution. And for frequencies that are smaller than the temperature, the Bose-Einstein distribution becomes much larger than 1. So it becomes approximated by this 1 over omega, or by this T over omega classical form. So they become classical fields. What does it mean, classical field? It means that the occupation numbers become so much larger than 1 that quantization effects become negligible, and you can think of them as classical fields. And this picture, which underlies weak coupling, has been applied in the case of thermodynamics to a large loop order. So this is probably next to leading order or something like that. So if leading order is order g to the 0, next to leading order is g squared, next to leading order is g cubed, next to leading order is g to the 4th, and this is g to the 5th. So I lost count of the n's, but there's plenty of them. And so you see here for the EQCD, it's really at this order, it's this band. And for the thermal loop perturbation theory is another approach to thermodynamics, which also relies on this picture, but which has a different counting of what you consider leading and sub-leading, essentially. So a different way of doing your summations. And this is compared with lattice data. So this is the pressure divided by the ideal gas pressure for a system at zero net baryon number. And you see here that even though the theory uncertainty for the perturbative calculations are large, they follow the trend of the non-perturbative lattice determination down essentially to at least 2 times the critical temperature. So here then you see that there is clearly a large deviation as the description in terms of quarks and gluons as degrees of freedom completely breaks down and you move into a hadronic phase. So in the case of thermodynamics, this is time-independent observable. So the pressure, the energy density, and so on in an equilibrium system, they're completely time-independent. And so these are kind of the simplest conceptually speaking. Technically, they're very complicated, but conceptually speaking, they're the simplest calculations you can do for a weak coupling system in thermal equilibrium. And as I said, many orders have been reached. Now, just to contrast, before I go into non-thermodynamical system, let me just give you one slide on how you can also do the same for at much higher temperatures. So in the context, for instance, of cosmology, you want to know how the pressure and the energy density and so on of the full standard model, for instance, behave at temperatures that are 1 order of magnitude larger, sorry, not 1 order of magnitude, but 3 orders of magnitude larger than that. Because we know that at the temperature of about 160, no longer MEVs, but GeVs, there is a crossover for the standard model, for the electroweak theory. So you see here, this is essentially the condensate of the scalar, so of the Higgs doublet. And you see that at temperatures above 160, this is negative. So it means that there is no expectation value for the Higgs field and you're in the symmetric field. So electroweak symmetry is completely restored and then it rapidly crosses into a positive expectation value. So it means you're going into the broken electroweak phase that we live in today. And again, these are perturbative calculations on the 2 sides of the transition, and it's only in a very small window across the transition where lattice input, which are the dots, really becomes important. And if you translate then this and you get all the other contributions and you compute the energy density and the pressure, you see that in this case, we have a precision that's much higher than what we have for QCD. If in this mostly perturbative scenario, there's still a 1% systematic uncertainty that's not shown by these bands, but still it's of course much better than what I was just showing before for QCD. And the message would be that in this case, we have a system that's where most of the degrees of freedom are actually weakly coupled, which is very different from what is happening for QCD close to the transition temperature, where again, the behavior is very different. So enough said about thermodynamics. Let's now introduce really time as a variable. And because we will be studying thermalization in the end, so then of course, time evolution is all the business. So then we're transitioning from thermodynamics to dynamics. And contrary to thermodynamics, where we have very good lattice data and we have perturbative calculations to high orders, in many cases, we are starting to scratch the surface of beyond leading order perturbative calculations, and getting lattice data is also a lot more challenging because of, for instance, reconstructing spectral functions from lattice data. So let me show some examples. What I'm showing here is kappa, which is the heavy quark momentum diffusion coefficient. So if you have a heavy quark in a plasma, how much momentum squared it's picking up per unit time. And you can see here that you have two different definitions of what you can call a leading order value. And already one becomes pathological at relatively intermediate couplings. So a G of order 1 corresponds to an alpha strong of order 0.1. So this is not really a very, that's still a reasonably small coupling, but already the strict leading order, sorry, it's already breaking down there. And then you have another definition from leading order, and then you have the next leading order calculation by Moore and Tini from about 15 years ago. And you see that it rapidly, completely overtakes the leading order curve. So you have one example where perturbation theory seems to be on thin ice in the sense that there is a large discrepancy between leading and next leading order, so that convergence is only realized at very small couplings. And you can think of this kappa as a non-relativistic counterpart to Q hat, which will be an important part of what I will be doing, what follows. So Q hat is the transverse momentum diffusion coefficient. So before you had a very non-relativistic heavy quark, now you have a very ultra-relativistic parton, quark or gluon, that's shooting through the plasma, and you want to know how much transverse momentum it's picking up per unit time. So that's the definition of Q hat. And yes, so that, of course, is something that I forgot to delete when I copied one slide over to the other. Sorry about that. So what I'm plotting here on the left is the so-called broadening or scattering kernel. So Q hat is essentially the second moment of this quantity. And here you can see what would be the shape. So essentially, to get Q hat from what is plotted here, you have to imagine multiplying everything by Q perp cubed and taking the area under this curve. So this is a plot that comes from Søren and his former student. And you can see that there is quite a big difference between the leading order value and the next to leading order value. And now it's even possible to complement this perturbative determination with non-perturbative determination of the classical contribution to this, which I will describe in a bit in the context of thermalization, what this means. And even though it might not be too transparent from this log-log plot, the difference again between the leading and next to leading order values for Q hat can be about what's happening here, so that next leading order will rapidly overtake the leading order. Then there are two more examples which come from my own work with my collaborators. So the one on the left is the photon production rate. So how many photons are being produced by an equilibrated plasma. And what's plotted here, it's a quantity that's directly proportional to the rate. And it's just more practical to plot this because, for instance, you can see what's happening without being drowned by the exponential suppression that's hidden here. And so if the dashed curve is the leading order curve, the solid curve is the next leading order curve. So in this case, it seems that next leading order is much better behaved than what was shown previously. But what we actually showed that this relatively small next leading order correction comes from two large, but also largely canceling next leading order corrections of opposite signs. And we think that the magnitude of the cancellation is largely accidental. So for instance, if you tinker a bit with the specifics of your theory, so how many colors and numbers of fermions and so on, the magnitude of the cancellation will change. So there's some element of accident in this cancellation. What I show on the right are the transport coefficients, in particular the shear viscosity. And in this case, this pattern of large corrections, which was lost here, comes back again, because if this is the leading order curve as a function of the temperature, and the band comes from essentially from the uncertainty in the running coupling, you see that even at temperatures that are of the order of the TeV, there's still a factor of 2 discrepancy between leading and next leading order. And if you go down to QCD transition temperature, this factor of 2 becomes a factor of 5. So also in this case, convergence seems pretty bad. And so that clearly motivated us to try and see if we could also apply this type of corrections to thermalization to see, for instance, how stable numerical solutions of kinetic theory are to possible large next to leading order corrections. And to do that, let me describe then in more detail than what I did last time, what is the effective kinetic theory, which is the tool you need to study thermalization at weak coupling. And it's a tool that has a very long story. Yes?
Yeah, sorry, before you continue. So I like your motivation that, look, the next to leading order contribution to these other processes is large, so we should think about this for thermalization. But is there also maybe even a danger that, oh my gosh, if the next to leading order term is so large, are we sure that the next to leading order term isn't either as large or bigger, and therefore that negates the whole expansion that we're performing?
Right. So very good point. Yeah. So I will try to maybe explain this as I go along, but I think the issue would be that in most cases, a significant part of the problem is due to this background of classical gluons, and which have large occupation numbers and can rapidly become non-perturbative. And so, for instance, if you look here at this plot of the burdening kernel, which then feeds Q hat, so you see here that at leading order in the infrared, you have this 1/q² limit, which comes from dealing with screening at leading order for the electrostatic modes and having no screening at all for the magnetostatic modes. Then, if you look at the next to leading order, you have the green curve, which is a 1/q³ power law. And it's the same power law that actually arises when you include the contribution of these classical modes to all orders through lattice calculation in EQCD, which is this, which are these dashed curves in here. So you see that even if the coefficient of the power law is different between the NLO and the full non-perturbative determination, the exponent of the power law is already the right one at next to leading order. So the infrared is a lot better captured by the next to leading order than by the leading order. So that could mean that maybe there's something that we're just not doing well at leading order, and that NLO already does a good job at changing that. That could be an optimistic take. A somewhat intermediate take would be that through the methods that are used to tackle the classical modes, you can do it non-perturbatively, and if you can, you should, which is what is done in this plot. That's good for Q hat. It would become a lot more complicated for thermalization because you don't have a thermal system, so it could be harder to do what is done here. There is some hope, but it's not clear. I mean, I've been speaking with Sir, and we will see if that's possible. But yeah, so I will try to explain a bit better in what follows what are these classical modes and why dealing with them with more information changes the results, and what are these next leading order corrections. So what the effective kinetic theory is as a very long story, and here there's a probably incomplete list of names that over the past 2 or 3 decades contributed to this story. So what's the main goal and the main ideas? So you want to describe, of course, excitations on a scale that is large compared to the typical de Broglie wavelength. So in equilibrium, that's 1 over the temperature. When we leave equilibrium, then we will not have the concept of a temperature, of course. So you should think instead of 1 over T, 1 over P, which is the typical, the average momentum of the particles in your kinetic theory, and that then once you reach equilibrium becomes something that is of the order of the temperature. So this kinetic theory will be obtained if you integrate out something from the full theory. So what you have to integrate out is quantum fluctuations which are of shell, and you can do that, for instance, from a Kadanoff-Baim set of equations. And then you obtain Boltzmann equation for the single particle phase space distribution. So as I said last week, dn over d3x, d3p is this f. So it tells you how many particles you have per phase space unit. So it's something that's dimensionless. And then you have that on the left-hand side, you have the convective derivative, which equals a collision operator on the right-hand side. And from that, you can also see what is the related condition, that is the underlying quantum field theory, which microscopically describes what's happening, must have well-defined quasi-particles. That means that the mean free time between each collision described by the collision operator, and then this mean free time is something that's parametrically of the order of the inverse of the collision operator, must be large compared to the duration of each collision, which is instead of the order of the inverse of the exchanged momentum in a collision, or for the more collinear processes would be the order of the formation time of the radiated gluon. And as I will discuss in a moment, there's another caveat, and that is that this kinetic description cannot be valid for any value of f, but it will only be valid up to some maximum occupancy, and I will explain why that is in a couple of slides. So then, of course, you can only have a kinetic theory once you really specify what is your collision operator. And the collision operator at leading order for QCD was derived by Arnold, Moore, and Yaffe 20 years ago. And it's made essentially of 2 components, an elastic component and an inelastic component. So the elastic component is perhaps what you would expect naively and what we also saw last week. So you have, for instance, here, hard gluons scattering with other hard gluons and exchanging momentum. So as you can see, this can be very efficient if you want to isotropize momenta, because this Q here is not restricted to be small, so it can exchange large momenta and deflect particles by order 1 angles, and that's important for isotropizing momenta. And we will see that in the context of thermalization in a few minutes. But then you also have these effective 1-to-2 processes. So these are not, strictly speaking, 1-to-2 processes, because each cross corresponds to scattering another hard gluon or quark in the medium. So these are always 1 plus n to 2 plus n processes, if you actually count the number of particles. And so normally these processes would appear suppressed by many powers of g, because here there's a g and a g, so oops. And then when you square this to get the matrix element square, this is of order g to the 4th, and this looks like it's order g to the some very high number. But the message here is that when this angle is small and the 2 particles, the 2 outgoing gluons are then very collinear, what's happening is that all the intermediate states are very close to the mass shell, so the propagators are very large and they can compensate the extra powers of g, so that these processes here will also be of the same order of these processes when they are these. And that's why we speak about them as effective 1-2 processes, because all these other ones are doing is just provide soft. So you see here, there's no line. It means that these exchange gluons are soft kicks that just allow this extra radiation to take place. So the fact that these are collinear means that they will not exchange a lot of momentum. So this will not be important for isotropizing momenta. On the other hand, first of all, they don't conserve particle numbers. So they will be important for chemical equilibrations, where you need to make sure that you really have the right number of gluons with a certain momentum. So you have to change numbers. And changing numbers might be more efficient than changing the momenta. So that can be important for chemical equilibration and for energy transport. So if you have to move fast energy from the UV end of the spectrum to the ER end of the spectrum or vice versa, these processes, which of course can take place in either direction, will be efficient at doing that. So if they go from left to right, they're efficient at moving energy towards the infrared. If they move from right to left, they're efficient at moving energy towards the ultraviolet. And so let's discuss now a bit more how you describe these processes. So for instance, the collision operator for the 2-2 processes, you can describe it as this, as we saw last week. It's a phase space integral that multiplies the matrix element squared for this process. There's a delta function for energy momentum conservation, some normalizations, and then the statistical functions. So this is now the moment to see why there is a validity limit in occupancy for the kinetic theory, and why that validity limit is that the occupancy F, so the distribution function, cannot exceed 1/g squared. Why is that so? Because we are doing a perturbative expansion to get the processes, right? So we're saying that this should be smaller than what happens if we have a fifth gluon in the process, for example. So adding a fifth gluon or another particle to the process, we pay a price of g squared. And so that will be a smaller correction as long as that is true, because when g squared f becomes of order 1, now this there would start to be an enhancement here to the statistical function, and we will stop having a perturbative expansion. So we will not just be able to say that the collision operator is just 2-2 and 1-2 processes, but we would have to consider all, so 2-2, 2-3, 3-3, 3-4, 4-3, and so on. And so it would be impossible to implement as a kinetic theory. You would have to use different methods, such as solving the classical equations of motion on a computer, because at that point you really have essentially a classical field system that you can solve classically, because you would have large occupation numbers. There's another point I want to make here. So you might have noticed that I've written the matrix element squared as a function of small m. And what is small m? So the point is that if you actually, if you try to do this integral here naively with bare matrix element squared, you get infinity. That is that you have, for instance, in the case of this process, which has an intermediate gluon, you have a matrix element squared that has a part that's proportional to 1/t squared or 1/u squared. And and when you are integrating over the phase space, you're also integrating over regions where t will become very small and u will become very small. Now, the numerator here will also become smaller because the loss and the gain term get very close to each other when the exchange momentum becomes very small. So overall, you don't have a 1/t squared, but you actually have a 1/t whoops, a 1 over t divergence, which is still a divergence, it's logarithmic. And so naively, the problem seems ill-defined because you get infinity, but it's actually, this divergence is there to signal, to tell you that you're doing something wrong there. So if you're going towards very small exchange momentum, it corresponds to saying that you're probing the medium at longer and longer wavelengths. And at some point, you stop seeing the medium as individual quasi-particles. You start to see bunches of quasi-particles. You start to see collective effects. And the first collective effects enter at a scale which is in equilibrium, g times t, and off equilibrium is this screening scale here, m squared, it's g squared times this specific integral of the distribution function. So what's happening here is that you're really seeing this physics of collective effects, and you have to amend your bare description to what is appropriate at longer wavelengths, which means in practice, and that was what was done back then, that you have to introduce hard loop resummation in the intermediate propagator. So this intermediate propagator will now be sensitive to collective effects once it reaches very small momentum exchanges. And that was worked out back then. And so that introduces the dependence on the screening scale M. So in equilibrium, this is just G times T times a number. Off equilibrium, it's something that depends dynamically on how off equilibrium you are. So you have to know what your F is at any time to determine what your screening scale is at any time. And for what concerns the collinear processes, what I haven't said yet is that I said that there are these scattering processes with medium constituents that induce this radiation. What I haven't said is that the mean free time between these soft collisions is of the order of 1 over g squared times the typical momentum in the plasma. So that would be 1 over g squared t in equilibrium, and it becomes comparable to the formation time. So the formation time is this quantum mechanical concept. So here I am emitting a gluon off another gluon. And when they're here, for instance, the transverse size of the wave packets are still overlapping. So when they're here, or when they're here, or even when they're here, the two particles are still not individually resolved. So the emission process quantum mechanically hasn't, how do I say it? It's still in process, so to say. It's only after the transverse, a sufficient time has elapsed for the transverse wave packets to no longer overlap, so that the two gluons have somehow decohered, that I can now think about the two gluon system. Before that, the process is still taking place. And what's happening is that if this mean free time between two of these collisions is of the same order as the formation time, which is what the box here highlights, then many of these collisions can take place during one formation time, and then there will be quantum mechanical interference between these collisions. And that is what is called the Landau-Pomeranchuk-Migdal effect. So Landau-Pomeranchuk and Migdal worked this out in the 50s for an electron that is shooting through a medium of nuclei. And so during the formation, if this electron is radiating a photon, while it's undergoing interactions with the Coulomb fields of the nuclei, it can enter a kinematic regime where the formation time of the radiated photon becomes longer than the mean free time between each successive interaction with the Coulomb field of the nuclei. And so to correctly describe that spectrum, one really needs to account for this effect. And then this has been extended to QCD in about 25 years ago by BDMPS and by Zakharov. So that was the big picture of the effective kinetic theory of QCD at leading order. Now, how does this connect to thermalization? So let me point here some reviews on the subject. And the main idea of thermalization is that there will be a competition between two opposing effects. On the one hand, you have that in actual heavy ion system, there is expansion, there's Bjorken expansion, so expansion in the longitudinal direction. And on the other hand, so expansion will want to drive the system away from equilibrium, whereas interactions will want to drive the system towards equilibrium. And there can be attractor solutions when they balance out. And this is related to the topic of hydrodynamic attractors in kinetic theory and holography, which is interesting, but which I will not have the time to discuss. So let's see how this works out in practice. So here I've written out in detail what the expansion term looks like. So it's essentially something that will redshift the longitudinal component of the momentum as time goes by. And so this is really driven by the specifics of the heavy ion collision, whereas interaction will tend to move us towards isotropy. So let's then see what happens and what is bottom-up thermalization. So this is a picture drawn, a sketch by Alex Ikurkela. So this is a plane. So the horizontal axis is occupancy, so the average F in your system. So you're assuming that you start out with an occupancy that is rather large, of the order of 1 over alpha. So this is an occupancy where the kinetic theory is at the edge of its validity. So in the earliest stages, you should not use kinetic theory, but rather classical lattice theory. So you start out with this high occupancy because the idea is that you start out with an initial state that comes from a color glass condensate description of the colliding nuclei. So the gluons are filled up to some saturation momentum that should be, in the end, larger than the final temperature that is reached at the end of the evolution. And the other axis is anisotropy. So it measures the ratio of the longitudinal to the transverse pressure. And so it tells you how anisotropic your system is. So initially, you also start out with some anisotropy, because initially your initial condition looks like that. So your transverse modes are filled up to some saturation scales, and your longitudinal modes are much less filled because of essentially the specifics of the collision and of Lorentz contraction and all that. Now, in the absence of interaction, what would happen is that the only effect would be the effect of expansion. So the longitudinal modes would keep redshifting. So this distribution would get even thinner and thinner. So anisotropy would shoot up without affecting occupancy, because occupancy is driven essentially by the transverse modes, and the transverse modes aren't getting redshifted. So in the absence of interaction, you would shoot up. In the absence of expansion, you would rather go kind of this way, and the two then tends to balance out on this first attractor solution, which takes you at increasing anisotropy and decreasing occupancy. So that's the first leg here. And so you're seeing it here. What's happening is that the effect of interaction is that it starts to isotropize the system. So it starts to move momenta that is initially quite anisotropic. It will want to isotropize it a bit, while at the same time expansion will want to anisotropize it further. And in doing so, it is also starting to create what resembles more and more of a thermal medium in the deep infrared of the system. Then what happens is that at some point, your occupancies become of order 1, then the same thing continues, but what changes is the slope, because when you hit order 1 occupancies, when the occupancies are larger than 1, the system is still kind of approximated by its classic nature. When it hits order 1, quantum effects take over, and that causes a change in the slope of the attractor solution. So that takes place here, and then you get to a point here. So what has happened here is that the soft thermal bath has now fully formed, and in the infrared, thermalization is faster, so it has thermalized. So you get to a point where you have a fully formed infrared thermal bath and an outer shell, which is the remainder of the hard modes that you had initially. And at that point, what's happening is that these hard modes are essentially propagating through this soft thermal bath, and you have some sort of kind of jet quenching scenario. There are sort of mini jets that are going through this soft thermal bath, and they're being quenched by it, and they're then losing their energy to the thermal bath, heating it up until you finally reach something, a final state here that is near thermal. So what's important then is that these first 2 phases are driven by the isotropizing effect of transverse momentum broadening. So here you have a system that's very anisotropic, and interactions isotropize it through transverse momentum broadening, which is described by Q hat. And later on, Q hat is also very important because these transverse collisions are what drive these effective inelastic processes, which are the driver of the final stage when the outer shell is being quenched by the soft thermal bath, and then it means that as it goes through it, it's forced to radiate extra gluons, it loses energy, it transfers energy to the thermal bath, and it heats it up to the final equilibrium state. So in both cases, the effect of transverse momentum broadening is very important. And in this case, again, these processes are rapidly transferring energy from the ultraviolet outer shell to the infrared inner shell without accumulating it in intermediate stages. And so that was a sketch. And it's actually surprising that if you solve the leading order kinetic theory, you see something that if you take a really small coupling, looks really just like that sketch. So that sketch came from order of magnitude considerations, and the full solution at really small coupling looks just like that. So this is from Kurkela and Zhu. Then if you crank up the coupling, the features of the sketch get a bit washed away, but you still see some of the main features even at a coupling of 0.3. And so on the right, you see then the evolution for a value of the coupling, which is again of the order of 0.3. So upper axis is time. And so these are some components of essentially of the energy momentum tensor. And so the full line is the solution of kinetic theory. And you see that at the time that it's a fraction of 1 Fermi over C, they're already pretty well described by hydrodynamics. So this tells you that even a weakly coupled kinetic theory can give a transition to hydrodynamics in a time that's of the order of the Fermi over C if you extrapolate to this kind of intermediate coupling. Now here I've said leading order a bit with an asterisk because there's a complication that I don't have the time to go through, unfortunately, which is essentially that as soon as your system is no longer isotropic, you have plasma instabilities. So this is a bit, this effect is not taken care in this leading order solution. I don't think I have the time to discuss this further. And I also shown this last week. So let's now use the final 10 minutes to describe next to leading order collisions. I'm sorry, I've been going a bit too slow. So in the following, I will concentrate a bit on an idealized case. So before we discussed the importance of anisotropy and of expansion. And here I will actually describe a kind of a toy system where there's no anisotropy. So the system starts out isotropic and there is no expansion. So if the system starts out isotropic, it will stay isotropic. And also I consider a pure glue system, but adding quarks is not a complication. I mean, it's not a conceptual complication, it's just a technical one. So even though this is a bit of an idealized system, it can still be some of it can be a kind of a good description of the latest stage of bottom-up thermalization, where you have this outer shell that's being quenched by an infrared bath, which has had already the time to thermalize. And for this ideal system, the full leading order results without any approximation due to the lack of plasma instabilities were presented in this paper from about a decade ago. And the reason we consider this idealized system, it's because in this idealized system, we have all the ingredients we need to address next to leading order corrections. So it's now time to describe what are next to leading order corrections and where they come from. So they come from soft gluons. So if in ordinary quantum field theory, if you have a loop like this, you pay a price of g squared. But at finite temperature, so this is in equilibrium, but I will now discuss why it also applies out of equilibrium. If the gluon is soft, so that it's in the classical tail of the Bose-Einstein distribution, if the momentum of the gluon is of order g times t, it becomes compensated by a factor of 1 over g, so that the correction is only order g. And if the gluon is even softer, the loop expansion breaks down entirely. Now, these next to leading order corrections are, for instance, what I've shown at the beginning for all these observables. And in the case of kinetic theory, they are known for the kinetic theory that's applicable to jets that are coupled to a thermal bath, or in a linearized kinetic theory that you use to determine transport coefficients. So why would these corrections be applicable to a system that's now very far from equilibrium in principle, where the distribution function really does not look like the Bose-Einstein distribution, kind of by construction, because you want to start out far from equilibrium and see how you get to equilibrium. So how come we can use those results? Because it doesn't look like that we could. Well, it turns out that 1 to 2 processes will very rapidly create and maintain such a soft classical bath. So before I've shown how the 2 to 2 collision operator looks like, and now I show briefly how the 1 to 2 collision operator looks like. It's a bit of the same idea. So you have an interaction rate, and then you have gain terms and loss terms. So this is a loss term. So you have P that goes into P minus K and K, and the inverse process. And here you have P that's absorbing K and going into P plus K and the inverse process. So that's the general structure. And why does this help us? It turns out that if you are radiating a soft gluon, then LPM effect is irrelevant, and the scattering rate is in the so-called Bethe-Heitler limit, so a single scattering limit. And there it's in a simple form that you can determine analytically, and you know that it has this 1 over P, so P is the momentum of the initial one, so it has this 1 over P behavior. So what's happening is that in this limit, where you have the process with the momentum much smaller than the typical momentum of the system, you can approximate the 1 to 2 collision operator in this form, and it turns out that it has a fixed point. So, oops. So you see that it has this 1 over P cubed behavior. So this will be very large at very small P, unless f of P in the infrared takes this T star over P behavior. So you can define this effective temperature T star as some ratio of some moments of the distribution function. And it turns out that this really enforces a fixed point in the collision operator, which rapidly makes the infrared tail of the distribution function takes this classical 1 over P form. And once the evolution approaches equilibrium, T star will approach T. So really, quite rapidly, you see in your numerical solution the emergence of that. So this is the results by Søren. So you see that initially there was essentially a delta function in the ultraviolet. But if you look already at the solution at the first time, you see that up here, there's a 1 over P power law. And this is maintained at all subsequent time steps shown in this plot. So really rapidly, you get a 1 over P infrared tail that you see in your data through the Bethe-Heitler limit of the collision operator. And so that makes it so that you can then take the next leading order corrections that came from this T over P soft gluons computed in equilibrium and just replace T over P with T star over P and take over those results. So those corrections then more specifically come both from 2-to-2 processes where you have to look in the region where Q becomes small, and then the process can be described as a diffusion process, which then becomes sensitive to longitudinal and transverse momentum diffusion. So here is where the isotropizing effect of transverse momentum broadening enters, which I described before. And for 1-to-2 processes, so here then the next leading order correction gives you these longitudinal and transverse momentum diffusion coefficients to next leading order with these classical gluon loops. And in the 1-to-2 processes, you have to determine this broadening kernel to next to leading order, so considering loops of classical gluons. And this is where you see the radiation-inducing effect of transverse momentum broadening. So in principle, this would have been horrible brute force high-thermal loop computations. However, we owe it to Caronio to realize that analytical properties of soft thermal amplitudes at light-like separations really make the difference here, because they allow us not to do brute force thermal loop calculations, but rather to get to analytical closed forms and to use the non-perturbative input. So the plot I showed at the beginning by Søren comes from exploiting the fact that really the hard light-like patterns sees these undisturbed soft modes because they really can't keep up with the hard patterns. So the response of the medium in this case is purely thermodynamical. There is not a causal response for these classical modes. And because of that, we have all the corrections. We need to get the next leading order corrections, which are then of this order here, which is order G squared T star over M, which in equilibrium corresponds to order G. There's an important simplification. Since we are isotropic, we will not be sensitive to the isotropizing effect of Q hat in the 2-to-2 processes because the system starts out isotropic and stays isotropic. So that effect will not be there in our system. Let me skip that. And let me just say that we will consider both underoccupied and overoccupied initial conditions. I'm sorry, for our numerical solution of this next to leading order kinetic theory. So in the underoccupied case, we have a Gaussian peak at an initial momentum that's much larger than the final temperature. And this is coupled to a thermal bath, which carries only a small fraction of the initial energy. This is mostly for numerical stability. And in the overoccupied case, we have a scaling solution that comes from classical lattice theory. So that's the plot I showed last week. So that's our initial condition in the underoccupied case. So this peak in the UV, and then a thermal a small thermal bath in the infrared, and that's the overoccupied initial condition. And as I was showing already last week, we see that as the time passes, there's a rapid transfer of energy between the ultraviolet and the infrared with this power law behavior intermediate, which is what is really related to this effective transport, which is happening to the 1 to 2 LPM processes, which never accumulates energy at intermediate stages. So you see, it's not like that the peak moves slowly until it becomes thermal. It's just that it gets depleted, but there is never accumulation at intermediate stages. And the opposite happens in the overoccupied case. The excess in the infrared gets transferred to the ultraviolet. And here I show the same results, but just multiplied by an extra p cubed, so that the area under these curves corresponds to the energy density of the system. Let me remind you that we are without expansion, so there's perfect energy conservation. Energy density, not just energy, but also energy density is conserved. And so here you really see that energy is rapidly being transferred from the UV to the infrared without accumulation at intermediate scales at any time. It's really, really clear what's happening. And the opposite is happening in the other case. So that's all interesting, but that's just next reading order solution. So how can we quantify what would have changed with respect to the leading order solution? Well, to do that, let us define a thermalization time as the ratio, as the time when the ratio between two moments of F becomes 0.9. It's an arbitrary criterion, but that's our choice. So these two moments of F would be both equal to the temperature in equilibrium. When the ratio is close to 1, we say that's our thermalization time. And so we show here plots of our thermalization time as a function of lambda. Lambda is the 12th coupling, so it's chi squared times mc. So the solid line is the leading order case, and the band here is the next to leading order one. So we have essentially two implementations of next to leading order, which somehow implement in two different ways. In one case, they resum some effects, so they are also a proxy for higher order corrections. And in another case, it's a more like strict scheme. So the size of this band could be a proxy of the tentative proxy for the size of even higher order corrections. And you see that in the underoccupied case, the corrections are really, really small, even at lambda equals to 10. In the overoccupied case, they are larger, but they still remain even at lambda equals 10 in a 40% range. And also in this case, the size of the band is much smaller than the difference with the leading orders. So that points to a well-behaved behavior in this case. So let's then compare this with the similar plot for the shear viscosity. So this is shear viscosity in a pure glue system. So it's an apple-to-apple comparison because it's essentially the same corrections, same theory. So in this case, it's 40% at lambda equals 10. In this case, leading order is here, next leading order is here. It's not 40%, it's a factor of 5. And so why does it look so different if, as I said, the corrections are the same? Well, they are the same, except that in this case, we started from an isotropic system. So the isotropizing effect of Q hat is irrelevant because the system is already isotropic. In this case, instead, the shear viscosity is really about damping shear flow gradients. So it's really about isotropizing momenta. So in the shear viscosity, the isotropizing effect is the most important effect. And actually, we can show that. So the solid green curve is the next leading order result. The band is a sort of a systematic uncertainty from us not knowing a part of the next leading order correction. And the green dashed line is what happens if you consider the leading order or collision operator and you just add to it the next leading order Q hat only. And you see that that's basically the whole story. So everything else is a small perturbation on top of it. So what drives the correction is next leading order Q hat, next leading order isotropizing Q hat. And in here, there is no next leading order isotropizing Q hat because there's nothing to isotropize. We are already isotropic. And let me also say that in the case of thermal photons and next leading order, that's also another calculation which is not sensitive to the isotropizing effects of Q hat. Whereas Q hat itself, of course, is sensitive to the isotropizing effect of Q hat, and kappa is the non-relativistic version of Q hat. So we might be seeing a pattern here, although we might also be looking at just a small number of calculations and it might be a coincidence. So it could be that the isotropizing effect of Q hat is the likely explanation for what drives the large corrections, or it could be that it's a coincidence. So far, we don't have that large pool of observables for which we have next leading order corrections. So that would be like my conclusions that have shown how for isotropic far from equilibrium system, it is possible to study the problem systematically and even to address higher order corrections. And also, as a final word of caution, care would be needed when using leading order kinetic theories when G squared T star over M is larger than 1. So I forgot to say it. It's indicated by this, I don't know if it's visible, this vertical gray line here corresponds to the line where G squared T star over M becomes of order 1. So above this line, you are extrapolating to the region where you wouldn't expect your expansion to be small anymore. And so that's when you should know when you're doing a leading order kinetic theory for heavy ions that you're extrapolating. So that's the criterion, so care would be needed there. And that's it. Thank you very much. And apparently I'm always timing my presentation to end at 15:06 or so. Sorry for going slightly over time.
That was great. Thank you very much. And we are always jealous of our speakers' time. So if you go over, that's actually great for us. So thank you. Questions from the audience. Yeah, Cole, please go ahead.
Those kind of like plots you've just been showing, I think I'm having a hard time interpreting exactly what's happening. In the previous plots you just showed with the, maybe a few slides. One or two more slides there. Yeah, so how do you use
this one?
The next one.
This one.
I'm not sure how to interpret the y-axis here because there's a few things happening with the lambda squared as well, and also you're varying lambda to x-axis. So I kind of understood the words you were saying, but I'm not really sure how to interpret the plots.
So I'm not sure I properly heard the questions too well. It's kind of, maybe if you move closer, I can hear better the question.
Yeah. I said, I think I understood words you were saying around this plot, but I'm not really sure I understand exactly why you plotted these specific things. Like, why are you varying with respect to lambda? And then why on the y-axis is it lambda squared times t?
Okay, yeah, sorry, indeed I forgot to mention that. So lambda is the coupling. Lambda is equal to G squared times NC is the coupling. So NC is fixed to 3 for us, just for practical reasons, but so lambda is the coupling, and we expect the thermalization time to be to be of the order of lambda squared times t, because lambda squared times t in equilibrium is the size of the collision operator. So the collision operator in equilibrium is of order lambda squared times t when you're in equilibrium or close to equilibrium, because if you look, for instance, at the collision operator, this one, for instance, as I said, m squared is of order g to the fourth, so it's of order lambda squared, and then you're you're working with a theory which is massless, so then the only scale you can have is t. So that's the expectation for the expectation is that this thermalization time should be of the order of lambda squared times t, and that it should also depend logarithmically on lambda, because there's the fact that you have this screening effect make the would-be logarithmic divergence that I was mentioning before when t goes to 0 or when u goes to 0 in the 2-to-2 processes, that is cured by screening. So that would be logarithmic divergence, now becomes a logarithmic enhancement of the order of lambda, logarithm of p over m, which in equilibrium becomes a log of t over g times t. So essentially a log of 1 over lambda, and that's what you're seeing here at small lambda. So that's why we choose this normalization for the vertical axis. If we didn't choose this normalization, the curves would be further apart, and I mean the curves for different q's and different lambdas would have different shapes, but we could have done that as well. And we want to plot this as a function of lambda because we want to see if we increase the coupling, if this picture breaks down. Say, for instance, what we saw for the momentum broadening coefficient, that instead of sticking close to each other, it could have easily happened that this would either turn backward like that or shoot up upward like this with respect to the leading order curve. And what I forgot to say is also that these are curves at 3 different values of the initial ultraviolet momentum. And what is plotted here is the same quantity, but not as a function of lambda, but for 3 different lambdas as a function of the initial ultraviolet momentum in the initial condition.
Yeah, thanks, that makes a lot of sense.
So let me follow up and ask, should I start thinking about this equilibration time as being associated with the tau naught from hydrodynamics?
Yeah. I mean, if you look at the plot I showed from Kurkela and Zhu, so he is really solving the order kinetic theory. Well, with this star here, there's an approximation to ignore the effect of plasma instabilities. Then he obtains the Fs, so the distribution function. Once you have the F, you can then compute the energy momentum tensor just by doing simple integrals and compare these components of the energy momentum tensor to what you would expect from hydrodynamics. And you see that second order hydro works till here essentially, and that's a fraction of a Fermi over C. So that's like, yes, this hydrodynamization time.
Okay, so yeah, I guess had always in the back of my mind that kinetic theory and bottom-up calculations just took far too long. But it seems like, do I understand correctly now, when one includes correctly the next to leading order?
Correct. No, this is Kurkela and Zhu is pure leading order. And it would be interesting to get the next leading order correction to this as well. And in this case, you would be sensitive to Q hat, so I don't know how things would go, but before you do that, you actually need to even, oops, sorry. You need to also address this that I didn't have time to discuss, this fact that this is leading order star, I called it. So, oops, apparently I paused sharing, sorry. You have to address the fact that essentially the treatment of screening in this solution is the screening that's appropriate for an isotropic system, even though the system is no longer isotropic.
How do you check how, how reliable that is then?
How do you check how reliable that is? Yeah, good question. Yeah, so what is shown here is that for at least for the initial, so because there was a whole debate about 10 years ago about the importance of plasma instabilities, and Kurkela and Moore argued that they would be very important. And then there was this set of solution of classical lattice gauge theory, so which are valid in the earliest phases of the evolution. And they all seem to fall on the attractor solution that was predicted by Müller, Schiff, and Son. So that's the original bottom-up paper. And that do not take into account the effect of plasma instabilities. So whereas these two curves that take into account the effect of plasma instabilities, they do not seem to attract the lattice solution. So either the effect of plasma instabilities, even though it's in principle parametrically leading order, it could be numerically smaller than expected. So that could be the reason also why doing this isotropic approximation to screening could not be such a bad approximation. But still, testing this beyond leading order will be very interesting, of course.
Good. Other questions? Maybe just a quick question from me. So maybe I missed the logic, but you said that for the soft emissions, it's in the beta Heitler limit, and I was surprised that it's not in the LPM regime. So is it that these are soft gluons, but they're emitted at wide angles?
Yeah, so what's happening is that they're really, really soft. So at some point, when the radiation becomes softer and softer, the formation time becomes shorter and shorter, because the formation time is directly proportional to the frequency of soft radiation. And at some point, it becomes shorter than the typical mean free path, so that you don't have time for more than one collision in the mean free time, in the formation time, sorry.
So is there some sort of finger physics that I should have in the back of my mind that says, you know, X is sort of a typical X and there's a typical K perp, and then I can see that XE over K perp squared is small.
So you should think about having so if both omega, is both omega and K perp that are of the order of the screening scale, then tau f, which is omega over K perp squared, is of order 1 over m, which is much shorter than 1 over g squared times p, because m would be of order g times p.
Right. Okay. very good. Yeah, so it's really dictated by G being very much less than 1.
Yes.
Okay, and then the awkward question that I'm always asked, which I always then, give a punt of an answer. So we're doing sort of thermal field theory under the assumption that G is much, much less than 1, but that G is sort of probably order 2-ish for the temperatures in phenomenologically relevant quark-gluon plasmas. So do you have a nice response to why we should trust these G much, much less than 1 calculations?
Well, I guess it might be a sort of a case-by-case situation, and there might be observables for which you can now at least try to get the classical modes under non-perturbative control, like it is being done for Q hat and for the broadening kernel. And yeah, so I don't have a one-size-fits-all answer to that. I think it might be that for some quantities you can get a good or decent perturbative descriptions, and others would really be dominated by non-perturbative physics.
I mean, is there maybe, so we do perturbative quantum field theory, and it's certainly, I do it all the time too. And alpha S is maybe not so large. Is there something maybe we can do besides hard thermal loops where alpha S is not too large, but G is not too small?
Yeah, so exactly. So that's, for instance, if you can treat the hard modes perturbatively, the hard modes have perturbative corrections, meaning that they go with powers of alpha S. So that would be reasonably described by perturbation theory, and the soft modes, or ultra soft modes, you would try to deal with non-perturbatively, for instance, using lattice, using dimensional reduction on the lattice, if that is possible.
Okay. Yeah, Herbert's face is, yeah.
A lot of stuff.
Yeah.
What can you do?
I mean, if it was easy,
Sorry?
we would.
Yeah, absolutely.
Yeah, Herbert was just saying it's tough, but then,
Yeah, no, yeah. Yeah, by the way, that is what is done also for the standard model plot I had at the beginning. This one. So in this case, you kind of have to do this if you want to do standard model thermodynamics, because even if you wanted, you cannot put the full standard model on the lattice, because we can't do chiral fermions on the lattice, and in the standard model, each chirality of fermions has different gauge assignments. So that's really important that you get that right. But the dimensionally reduced effective field theory doesn't have fermions at all. So that's no problem at all. And that's what gives these lattice points here on the left.
Very nice. Yeah. Yeah, whether this works.
Yeah, I'm not doubting that it works, right? It's just okay. Sometimes little miracles.
Yeah. Okay. Any last thoughts, questions? Yeah. Well, so thank you, Jacopo. Thank you so much.
You're welcome. It's been a pleasure.
It was really tremendous, and yeah, thank you very much, and looking forward to seeing you again, hopefully soon.
Looking forward to it as well.
Super. All right. Take care.
Bye.
Bye.